working group.
Thank you, Kristen. Yeah, we had a working group, Arctic change and possible influence on mid-latitude climate and weather, and then hard to believe that it's, I guess, in the sunset phase of the working group, and we're wrapping things up. But still plenty to do. So so get kind of to the punchline right away, in case people kind of start to drift. There's certainly one theme that has been common, throughout the working group's history has been that of uncertainty. This idea how much, if any, the Arctic is influencing mid-latitude weather. There seems to be no consensus that's been reached among the modeling studies. Again, these are the conclusions that have come out from the working group. There remains quite a bit of uncertainty surrounding the dynamic processes linking Arctic and mid-latitude weather, and this has had an influence of trying to evaluate model performance. What metrics to select to see what the models are. I don't know the word I'm saying, illustrating, but what they are teaching us about Arctic mid-latitude linkages. And there's been uncertainties exist in defining and prescribing the forcing that should be used in GCM experiments, whether they be atmosphere or coupled experiments. We know the models are not perfect. There are biases, systematic biases in the models, and we do not have a good understanding of how those model biases or deficiencies, have influenced the modeling studies, published so far. And also, it's not, it's not one direction, and separating out, how much is it, the Arctic influencing the mid-latitudes, or how much it's really just the tropics and mid-latitudes influencing the Arctic, and maybe some feedbacks, but all that remains quite unclear. It's certainly a challenging topic. And we've proposed that we should synthesize new Arctic observations, extend observational data sets, and include new observational methods. So we just had a white paper that was published just a month or so ago, and certainly one of the with these recommendations and certainly new observation methods. I know there was an emphasis on unmanned aerial vehicles, I guess drones and balloon launches, so things like that. But also there's something that's come out of this working group effort has been a coordinated modeling experiments and analysis. So instead of comparing apples to oranges, among different modeling studies, we're comparing apples to apples and oranges to oranges. So all the models are forced. They're the same design. The forcing is the same, and we analyze the same metrics. But it involves many different modeling groups, and we, as members of the working group, proposed a MIP project, polar amplification, model to comparison project, and it's been accepted, and there's actually a paper now out to review describing the setup of this PA MIP. So just getting into a little bit more detail here about this PA MIP, and it's being led by Doug Smith at the UK Met Office. So where we would have control runs, where we'd have sea surface temperature with force with a pre-industrial, and then future 2-degree warming of sea surface temperatures, or I guess of the entire globe. And again, we would have these AMIP type runs, so lower boundary forcing, where sea surface temperature, Arctic sea ice concentration, and at first I guess we were thinking of just doing Arctic only, but it was also recommended to bring in the Antarctic. So it's not just northern hemisphere, but southern hemisphere as well. And these AMIP type runs will be forced. The sea ice and the sea surface temperatures will be forced with pre-industrial and then 2-degree warming. and then not just have these AMIT, but also fully coupled runs, again with force with pre-industrial and then future 2-degree warming sea ice concentration, both the Arctic and Antarctic. So, and just a little context about the subject. We all know that the Earth is warming. It's pretty much warming universally across the globe, and there's been a very consistent over the period of observations. That it's been warming, and there was this hiatus. I guess there've been a few hiatuses. The most recent, in the 2000s, but I think most studies now conclude that that hiatus, if it existed, is certainly over. But so we have this warming, and with that warming, I guess have on the side, but really not that really applicable to my talk here. But the warming comes less snow. But again, on the slides I'll bring it up, but I'm not really going to touch on it again. And with that warming comes changes in extreme weather. So I know maybe some of you on the phone, at least Xiangdong was in Davos, so there was another meeting in Davos, a famous state meeting, the World Economic Forum back in January. And at the World Economic Forum, the economists considered that extreme weather is the biggest global risk. And that you can see here, up here, this teal or turquoise dot. Extreme weather, and that's followed by natural disasters. And here's on the right is a plot from the NRC, right, from the National Academy of Sciences, the National Research Council, that when it comes to extreme weather, the extreme weather that we're most confident will be impacted by global warming is a decrease in extreme cold, and then that's followed by an increase in extreme heat. And then you can see further down also extreme precipitation, where you have an increase in extreme rainfall, but you also have this increase in droughts. But again, I think it's, to me, it's interesting that the one extreme weather that the scientists, at least from the NRC report, most confident about is a decrease in extreme cold. Now, this is just some headlines from this past winter, towards the end of the winter. A lot of it's related to this polar vortex breakdown that happened in November, and then the extreme weather followed. So this whole topic of the Arctic, maybe linked with the polar vortex and extreme winter weather, severe winter weather, was certainly a topic that was, we call a hot topic, when we started, but I think, that hasn't, the topic has not, pardon the pun, hasn't cooled, over the tenure of our working group. And if anything, I think the interest has only grown. Okay, so again, I started off showing that we all know that the Arctic is, the globe is warming, but that warming is not uniform. There is variability in that warming, and the warming is supposed to be greatest over the Arctic region, and I'll show that in a minute. And our thinking was, at least early on, when people first started, supporting, analysis of this Arctic amplification, that it would be due to decrease in the cryosphere. We'd have less sea ice, we'd have less snow cover, sea ice, snow cover. You have albedos ranging up to about 80%. Where they reflect, 80% of the incoming solar radiation, and then if you peel away or melt that sea ice and snow, now you're down to a surface that has 10 or 20% albedo. So much more of that incoming solar radiation is absorbed at the surface, leading to warming. And you can see here is just so September sea ice in blue, and the June snow cover. I think it's for the whole northern hemisphere in red. They're both showing, quite a dramatic decrease. Sea ice has gotten certainly the most of the attention, but the spring, northern hemisphere snow cover, spring into even early summer, has been as dramatic, if not more dramatic, than the sea ice, but has gotten less attention. And that's thought to cause, a big part of Arctic amplification, but over the course of our working group, it certainly seemed to be more accepted that it's a much more complicated problem than just melting, components of the cryosphere. And it's just really just an example. And again, our white paper goes into detail about the contributions to Arctic amplification, but again, it's not just a sea ice problem. That the lapse rate also is contributes at least as much to the Arctic amplification. The Arctic lapse, the lapse rate in the Arctic is at least as big a contribution as the change in albedo. But there are other things, including increased water vapor and more clouds, which though is quite a bit of larger uncertainty. And then something that I think we talked about in our workshop, and again a lot in the in the white paper, is this transport of heat from lower latitudes into the Arctic, whether it's in the atmosphere or the ocean. So complicated problem, a lot of different components, and also large uncertainty. But so this is really now the focus of our working group, was about this interesting problem, interesting pattern, that I'm about to show you. This what's been coined, and I think it's become more and more popularly used, this warm Arctic cold continent, or warm Arctic cold Eurasia. I got a couple of mascots, trying to illustrate the warm Arctic and the cold continent. But again, what I showed earlier was the temperatures for annual temperatures, but I'm really going to focus on the winter, and maybe a lot of you here on the call already familiar with this figure or other similar type figures. But the warming, it turns out, is not, again, uniform. It increases, it's amplified as you get closer to the North Pole. And here on the left is the trend by latitude, the temperature trend by latitude. And you can see this weak warming is in the lower latitudes, and then that ramps up or increases, and then greatly is amplified as you get closer into the Arctic and closer to the North Pole. And this is what we refer to as Arctic amplification, where this generalized global warming is amplified in the Arctic. And if you look at the time series of where it's broken out between the Arctic in red and the mid-latitudes, or the rest of the hemisphere in black, for much of and going back to 1960, which is the trends here from 1960 to 2013-14, the trends were quite actually similar, the temperature trend of this annual time series for both the Arctic and the mid-latitudes, though the Arctic has greater variability. And only it was starting around 1990 or so did these two time series start to diverge, where the Arctic became, again, experiences as amplified warming. And if you redo the winter temperature trends only over that period of real Arctic amplification, you get this surprising and quite different pattern, where you certainly see now you really see that Arctic amplification more clearly. But in the mid-latitude continents, you see the regions of cooling. It's strongest in Eurasia, over the Central Asia, but also includes the Eastern United States. And if you look at the temperature trend with latitude, there's slight warming in the low, in the tropics and the low latitudes. There's this real amplified warming in the Arctic, especially as you get close to the North Pole. And then there's this surprising cooling in the mid-latitude belt. And this is why, again, this is what really was the focus of our working group over the past 3 years. What is the relationship? Is this just coincidence or random, this warming and cooling, or are they related? And is possibly this cooling being forced by this Arctic amplification? Just here's again an update kind of to these time series. The Arctic is in blue, mid-latitudes are in red, and then I show the difference in Arctic minus mid-latitudes in green. And this past winter, that Arctic, if you call this, if this is kind of a metric of what we'd call Arctic amplification, it'd be good to find different ways. This was this past winter was the greatest value we've seen over the entire, over the observational record of this Arctic amplification. So certainly something that seems to be getting stronger, not weaker with time. So so again, what are is there some dynamical relationship, or is it just merely a this correlation, this random correlation? So there have been many theories. The theory that has been, I think, has gotten maybe the most certainly media attention, and it's certainly got a lot of attention even in the science, in the scientific literature, has been this idea that this Arctic, since the jet stream is related to the latitudinal temperature gradient, that if the Arctic is warming faster than the lower latitudes, then the jet stream would weaken, in the westerly direction. This westerly westerly jet stream would weaken, and then that wouldn't be the only kind of changes to the jet stream. If it weakens, then then the waves would slow down. That maybe the waves become more amplified. You would get increased, maybe a decrease in the zonal wind, but you get an increase in the meridional wind, and that could lead to increased extreme weather. You have more amplified waves, slower moving waves, and greater north to south flow. But as a group, I'm not going to get into today's short talk, but there are many different theories put out to how maybe the Arctic can influence mid-latitude weather. But as a group, we concluded that if there's a dynamical linkage, the one that we're most confident is real, right, and not just some kind of artifact of chance or randomness, is that sea ice loss in the Barents-Kara Sea, and again, just like the warming isn't uniform, so sea ice loss is not uniform, but there are regions in the Arctic that have seen the greatest sea ice loss, and certainly in the late fall and in the winter, the region that has experienced the greatest sea ice loss is in the Barents-Kara Seas, and sea ice loss there seems to favor dilation of the geopotential heights. So you get stronger high pressure in that region, and it's sometimes referred to as Euro blocking. And if you get then you get this Euro blocking, you then tend to get you force a downstream trough over Asia, Central and East Asia, leading to cold temperatures there. And again, you saw in that previous plot that the strongest, and it turns out statistically the most significant cold across the hemisphere over the past 25 years or so has been here in the Central Asia. So this kind of connection between Barents-Kara sea ice loss, Euro blocking, and cold Asia, cold Siberia, sometimes people call it, we're the most confident that is real. Now we really focused on winter. But some of the people in the group have focused on summer, and there's a review paper that's coming out just limited to the summertime linkages. But some that really we didn't deal with that much, during the tenure of the working group. But there is a paper that deals with that. And so I've studied snow cover, but even sea ice, we've I think of it very much adopted this connection now to the polar vortex. Certainly seems to be an idea that has been gaining out of popularity is the right word, but certainly more and more studies coming out that it turns out that if you force that Euro blocking, or that blocking in near the Barents-Kara Seas, maybe over towards Scandinavia with this downstream troughing, that turns out to be a wave pattern that projects onto the climatological standing or planetary waves in the northern hemisphere winter, and is most favorable for exciting this vertical propagation of wave activity flux or Eliason palm flux, and then that, if it's absorbed in the polar stratosphere, leads to a weakening of the polar vortex. Most dramatically, maybe it's a polar vortex split. But we get this weakening of the polar vortex, and then when the polar vortex, is disrupted or perturbed, you tend to get this southward shift in the jet stream. This allows cold air outbreaks to lower latitudes. So here it's showing in this cartoon or schematic is showing most clearly Eurasia, but it's also happening here on the other side, across eastern North America. And not only do we sometimes get the cold outbreaks, you also get an increased probability of snowstorms, across the across the mid-latitudes across the continent to the mid-latitudes, including Europe and East Asia and the eastern U.S. And certainly we had a very nice example of that this past winter. But again, this is not a topic without its challenges. So some of the challenges that we discussed in the group were there's really a scarcity of observations in the Arctic. I guess at one point someone I was surprised to learn Arctic is the least observed part of the globe, and that even includes Antarctica. Also, there's a very short time series with the observations. Again, if we consider 1990, or not, some people like to consider 1998 as the beginning of Arctic amplification, these 2 to maybe 3 decades of data, a very short time period to do statistical significance on it. As again I touched on it, we do know there are model deficiencies. What exactly they are, I think we're less certain of, but the models are not perfect. Up till now, we've had uncoordinated modeling studies. So are we really comparing? And the models can be diametrically opposed. Let's say just for example, picking what would be the AO response, the Arctic oscillation response to sea ice melt. We have models say that there would be a positive AO forced by sea ice melt. We have model results saying there should be a negative AO, and some models say there should be no change in AO. So it really runs the whole spectrum of possibilities. So, but these models were not, they're not coordinated. The forcing is not the same, and can we compare these very different model results and conclusions? We know there are also biases and uncertainties in the metrics that you use for making these analysis, and certainly again something I touched on before. It's a very complicated system, climate, and exactly attributing what is the source of changes, whether it's from the Arctic itself or really what we're seeing, including Arctic amplification. Is it something that's being forced mostly inside of the Arctic, or is it a lot of it coming from outside the Arctic? So it's very complicated, and disentangling all these related components is a challenge. Again, this just applied from the white paper, just showing you here's showing all the different observation stations. It's not very much across the Arctic basin, really quite few, and certainly has made this problem a challenge. Again, it's not there are many moving parts in the climate system, and disentangling and attributing forcing to one part of it has been tough. So there's Arctic amplification forcing on the mid-latitude weather, but there's also other parts of climate change going on, and there's obviously a big problem has been natural variability, which includes internal climate modes, solar cycle, even volcanic eruptions. It's been tough to disentangle, and maybe the greatest source of disagreement among the different members of this working group. There are some recommendations that have come out. These are for coming out of the observational scientists most involved with the observational analysis or taking observations, is what their recommendations were for progress on this topic: to synthesize new Arctic observations, to create physically based sea ice ocean surface forcing data sets, mostly to force models with, to have uniform forcing data sets for the models to use, systematically employ proven and new metrics. There are new, I think this is about to come later. Also, one way to extend the data set is not just to limit ourselves in the past 20, 30 years of Arctic amplification, but maybe to bring in paleoclimate data, or even look into whether a similar type, we notice similar type temperature patterns across the hemisphere, like I think in the early part of the 20th century, to extend the observational data set. There's been, over the past few years, this realization there are new observational analysis methods that go beyond just showing a correlation. Like causal networks, where you could actually use these observation analysis to make statements about cause and effect, and to consider both established and new theories of atmospheric and ocean dynamics, to interpret and guide observations and modeling studies. The recommendations coming from the modeling side was to establish a modeling task force to plan protocols, forcing and output parameters for coordinated modeling experiments, and I talked about that at the at the beginning of the talk. And we have this effort underway, this PA mid-polar amplification model comparison project, and all the data set that will be generated from the different model incentives will be provided to the community, furnished experimental data sets to the community through open access, this Easy Grid, I think it's called, Easy Grid, or System Grid, similar to like the other like CMIP models, and promote analysis within the community of simulations to understand the mechanisms for Arctic amplification and to further understand pathways for Arctic mid-latitude linkages. So that'll be coming out over the next few years. The modeling results and then the analysis of those models over the next few years, and hopefully that will help us make progress. I think that's the end of my, I guess tout the accomplishments of our working group. So I think over the tenure of our working group, we've come to a better understanding and appreciation of the contributors to Arctic amplification. It's not just sea ice melt. And as a group, I think everybody that was involved in our workshop, we had over 100 scientists, everybody would agree, yes, the Arctic is influencing the mid-latitudes, but is it a significant or insignificant influence? And what exactly that influence is, I mean, there was no consensus. There is growing confidence in some of the proposed mechanisms linking Arctic amplification with latitude, whether specifically the one that we're most confident was that increased blocking or increasing high pressure over that Barents-Kara Sea Urals area with downstream troughing across Asia. We had discussions and then the white paper, and we still plan a review paper. This included both modelers and observationalists, so it wasn't just one group or each group issuing its own kind of set of conclusions and recommendations, but we came together as a group, and I think it was important. That was very nice that we had both the modelers and observationalists contributing equally and spoke hopefully with one voice. And we've made recommendations for both improving the observations and modeling experiments. And really, I don't know, it's the last task of our group. We're hoping to have a nature collection on the topic. That will be headlined by a review paper. The editors of Nature, I know, are eager to get this thing launched. They say late summer, probably not going to happen, but even if it happened in the fall sometime, that would be nice and nice timing, since so much of this involves winter weather. So now I think, and there was also talk of maybe doing a special issue in let's say like an AMS or AGU journal. So we'll see if hopefully that'd be nice if we can get that together as well. Okay, so that was really that's the end of my talk. Thank you very much.
Great. Thanks, Judah. We can take any questions now from folks. Just a quick reminder, raise your hand and I can take you off mute and you can ask questions. So before we get any questions and people are raising their hands, I've taken, Xiangdong, you're off mute. Did you have anything you wanted to add to Judah's presentation?
I think that Judah's presentation covers everything for the last 3 years' effort in this working group. It's pretty good. Actually, there's one thing I would like to add. So the U.S. collaborates working group as a part of the organizer for other smaller workshop in Colorado last year. So there was a summary about the fully coupled model. So there has been emergency of some consistency across across the different fully coupled model in response. I'm talking about the atmosphere circulation in response to sea ice forcing. So that's a part of progress on the topic. Thank you.